I have to.
Yeah. You know what the chances are though? Chances are I'll cut it and I'll wear this, you know, and somebody will pull it up and it will just fall.
You are in a medical mirror. I'll take it. Hey, every point, man. Alright guys, I think since I said earlier something about saddle point, you all kind of knew what I was talking about. Or at least you pretended you did. You saw everybody else around just shaking their head. So I think last time I did make it up to the basic definition of saddle point. Right? No? No? I think it was right ahead. Alright.
Fail.
Everybody that thought they knew it, was lying. I like that. So we did get it 12.8 last time, right? Yeah. Because I did say the really basics, I mean the stuff we kind of know. If there's a local max or a min at a point, then what must be true at that point? If there's a local max or min at some point A, B.
Then F of X.
Partial of X.
Partial of Y equals 0. I love how everyone says it differently.
It's the same answer.
I like it. Yeah, there's a million different ways to say it. Does it work the other way around? No, of course not. But what do we do this process for to find? Do you think? What are the candidates for being extreme called? Critical points. I love it. So that's the same as it was before. I still find critical points. I just have to use partials to do it. So it works this way for sure. The other way is just a candidate. Yeah, every single place that there's a local max or a min, this must be true. But not every single place where this is true is there a local max or min. Because it could be one of those psych out things, right? We already said about if there's a tangent plane somewhere. If the tangent plane exists at an extrema, what must be true about that tangent plane? It's got to be horizontal, but it doesn't work the other way around. If the tangent plane is horizontal at a point, again, it could be a psych out point, right? And I think I did define critical points here, right? Yeah, we did. Because critical points, of course, occur, like we said, either where this is true, and of course, this is kind of assuming as long as f of a, b exists, right? Because how do you find critical points? They are where this is true or the function is undefined. I love it. So critical points exist where this is true, or they are cool. So that's, I guess, where I left off right there. So a saddle point, the definition of a saddle point, and then we'll talk about how to find all these things out. What are they? The saddle point is a place where there are certain elements. So it's if you have a region in your XY plane, right? So I'm always talking about my inputs. If there's an output where some things are lower than it and some things are higher than it, but there's a horizontal tangent there, then that's a saddle point, right? And that's on page 855. Is right where I am. So if I have a critical point. This is a critical point. And f of xy greater than this at some points. Right, so some points near AB, if this is greater than this, and at some points near AB, this is less than that, then that's the saddle point. So look at the 2D analogy to this, and I keep going back to my cubish dude, right? Yeah. So this is cubish. So right there, this has got a critical point at 0. And certainly there are some values that are higher than it, and there are some values that are lower than it, in a neighborhood around it. That's really all this is saying, but in more dimensions now, right? So that's why the saddle point, the picture that people normally think of, is the one like on page 855, where in one dimension I'm going this way, and in the other dimension I'm going this way. So on my x, let me see which way I want to go here. Oh, this is a horrible 3D picture.
It's okay.
I'll somehow live x, y, z. So on the maybe this plane I'm going up, and this plane I'm going. So in my y, z plane I'm going up, and maybe in my x, z plane I'm going down. And you can see that, of course, much better on the picture they have. Their computer-generated pictures. I don't feel too jealous. Right, this way it's going down, this way it's going up. Exactly like a saddle. So the real question here is the place where things definitely get different. Because so far, hopefully you notice they're not all that different than they used to be. They really aren't. This saddle point is somehow related to an inflection point kind of idea in a way. So here's where things get seemingly different. What did we use the second derivative test for before?
Concavity.
Concavity. Of course, if I know there's a critical point somewhere and it's concave down there, it's a max, right? Remember, just cut down, that means it's got to be a top of the hill. Of course, if it's concave up, it's a min, right? Yes, ma'am.
Can you finish that sentence right there? Because, so if that's true, then what?
Oh, then, sorry. Then A, B is a saddle point.
Okay. And saddle point means that,
Saddle point means this.
okay, so this is just saddle point.
This is the definition of saddle.
Okay, so we just,
Cool.
if we have something like that, we just write saddle point, that's it.
I like it.
Okay, cool. Moving on.
So, I've actually got to be careful. This is why I don't teach English. Right? But in math, you still have to be careful with how you say things. And let me kind of turn this around. This is why I didn't really finish it out. If I do have a saddle point, then this stuff is true. It's sort of like earlier. If I have a max or a min, then fx equals fy equals 0. But not the other way around. So it's not ever quite as easy to find these maxes, mins, or saddle points, because I can find where they might happen, and I need something else to help me figure out if it actually did happen. You with me? So if I do have a saddle point, then this stuff here is true. Okay? Just like we did in Calc 1. I want to try to use a second derivative test. Now in here, obviously, it's going to be more difficult, because with partial derivatives, how many second derivatives can I have? So if I can take the first derivatives, fx and fy, what second derivatives can I make? Yeah, fxx, fxy, fyx, fyy. And of course, these are normally the same as long as those derivatives are continuous, right? And normally they are. We normally look at decent functions, right? They will be continuous on their domain. So normally that's those are the same. So what we do is we define something slightly funky, and I'm going to try to make it make some sense as to why it tells us what it does. We define this thing. I'll use the same. Okay. So define d of xy equal fxx, fy, minus fxy squared. Now, I want to kind of use this as an example. Let me see, I need a couple examples here. If I had something that was obviously a min, so I'd have something that was like, and again, Jeff, you need 3 dimensions here. So I have something like this here. We actually did one like this a while back, where it's parabola there, and it's parabolic this way. So it's just going forever up. Right? You guys kind of with me here? Horrible picture, but oh well, too bad. So it's just this big, open, weird ass looking, you can't balance it worth anything trash can, right? Boom, it's not really a good trash can at all. What's definitely true about that point there, of course, that is a min. In the x direction, what would the second derivative be? What would fxx be? And using what you know, don't tell me what it is physically, tell me what it is that I care about. I care if it's positive or negative or zero, right? Because if it's positive, it still will mean concave up. If it's negative, it will still mean concave down. And just looking at the picture, it's going to have to be positive, right? So thank God it really means, because again, the beautiful thing about partial derivatives is they allow you to think two-dimensionally. Because you really are holding one constant. You don't have all three dimensions going on at once. So it is exactly the way it used to be, thank God. If this is positive, and fyy is positive, at some point, what do you think pretty much has to be true? What do we see here? It's got to be a minimum there, right? So if I have a critical point at some AB, and this is true for that point, it's got to be a minimum. And of course you can see if it was less than 0 for both, it would have to be a maximum, right? Same idea. So that's where it's the same as it was for us in earlier calculus courses. So let's see why this thing captures that idea. Here are the main steps here, know how to interpret what this tells me. So if I do this at a point, and I get, where are my little notes? All right, so if this is greater than 0, see, I want to do in the same order. Yeah, okay. And this is less than 0. And again, what does it mean then if fxx is less than 0? Now, I really want you to think about what this really means. It's kind of funny the way they say this. What they're really trying to say, can somebody tell me mathematically, does what I've written up here, what does it say about fyy? Why would fyy have to be negative? So it needs to be positive, which means this piece has to be how related to this piece? Has to be bigger. So can fyy necessarily be negative? The easiest way to make that happen is to have, I'm sorry, yeah, in this case, sorry. So fyy, I'm thinking ahead to the other, has got to be less than 0. Because then what does that make this piece altogether? Positive. I love it. So you're right, don't worry. I think this whole thing at once. So that's why they don't have to mention fyy here. It kind of inherently means something about that. And what did we just say related to what we did there? This was an example where they're both positive. So it's cup up, so it's a minimum. What's got to be true for this guy? It's got to be a maximum. Cool. And again, this is page 855. So this is my own little addition, right? This is my addition to the book language. But it's not necessary because it kind of implies that. It means that that's got to be true. Then, f of AB is a local max. Or a local max is at the point AB, right? You want to say it that way.
So it concaves down.
Yeah, in this case, it would be concave down, and that's why it makes sense that it's got to be max. How are we doing? So in one sense, it's kind of nice. That means that no matter which direction you look, it's somehow concave down. Maybe it's concave down more in some directions, but that means that's got to be a top. That's got to be a maximum. So what do you think the second case is? This is positive, but yeah, fx is greater than 0, and this is the case I was thinking about earlier. That would imply that fyy also has to be greater than 0, and that's exactly like the situation we saw over there. Everything's going up away from it, so this point must be a minimum. And there's a local min at AB. Cool. where things deviate. I mean, so far we said that the d is greater than 0. So what the hell happens when d is less than 0? And let's really break down what that would mean. If d is less than 0, that means that fxx, y is less than fxy squared. Right? Now, just to kind of get past all the technical ways to make this happen, the easiest way to make this happen, and the only way I'm going to talk about right now, is if these two are what? This guy is definitely always what? Positive. So these two somehow have to multiply by a. So these two have to have opposite signs. And isn't that exactly what I was talking about earlier for the occurrence of a saddle point? If you look in the x direction, it's concave up. But then you look in the y direction, it's concave down. That's a little tricky point. That's a saddle point, right? So if d is less than 0, no matter what the hell these two are doing, that implies that that's a saddle point. Then there is a saddle point at AB. And finally, from what you guys did in Calc 2, you know that these tests nowadays have these evil inconclusive parts. And of course, inconclusive here would be when D is, what have I left out? 0, cool. So that's the last piece here. If D is 0, inconclusive. And too bad for you. Okay. And it's really not difficult for something to be inconclusive. If you have the picture, you're like, well, obviously it's a minimum, but then the math says, I have no idea. You know, and it's like, well, it's too bad for that. But we know it's kind of like where that gets really kind of flat. I can have inconclusive tests where it's kind of flat, because then it's not really easy to tell, and in a local area, is it going up or down? The test kind of goes, I can't tell what's going on there. It gets kind of flat right there. I don't know what's going on. So that's when that happens. That's too bad. So let's try some specific problems out then. And you start to see a plan of action here, a way to attack the problem. You got a ton of little pieces to put together. Your first step, before you even really get into these, is to find what? Well, even that, why are you doing that? To find the places where these might happen, so to find the critical points. Exactly, cool. Just like back in Calc 1. You got to find your critical points first, and then you apply this test to them. So, let's do a slightly more interesting problem here than the next example. Let's do example, which one was more interesting? Oh, that actually, example 3. So if I have, where'd it go? Let me show you guys a little something here on the side. Isn't this the same thing as x times x minus 2 times y squared plus 3y? And isn't this the same thing as y times y plus 3 times x squared minus 2x? Right? So these actually become very handy when you're doing some of these derivatives. Because in this case, if I do fy, why is this written really nicely? Because this piece would be, careful, a constant, right? 0 if I was doing some crazy product, I don't have to do the product rule because this whole thing is a constant. It's like 5 times this, so then I just have to focus on taking derivative here. I don't even have to factor at the end. I don't have to do the product rule all the way out, right? Here I've got to do the product rule. Here, I don't. So there's a little suggestion I have for you about rewriting it to make it easier to do the derivatives. So how do you find the critical points? What do you do? So what equals 0?
Fx, Fy.
Fx and Fy, I love it. Right? Just like in Calc 1, you got to find the slope, and then the slope equal to 0. Okay. So let's see if you guys, so figure out what fx is, figure out what fy is. So fx is pretty easy now that we've got this here, right? Ignore, fx is blah blah times 2x minus 2. So you get twice y plus 3, x minus 1. How's that? Is that cool? Don't have to do that, but I did. What's fy going to be then? Same idea, right? This and this are constants, you get 2y plus 3, right? So x minus 2, 2y plus 3. Now here's the part that I really want you guys to understand. We have a system of equations here. I have to work between the two of them to fill out all possible points. And of course I want to do what with each of those? So that equal to 0. So you pick one of them. Let's do the first one, I don't care. What are my answers to this? 1. Now you plug each of those into the second guy because they have to make both of them work and see what you get from doing that. So if I plug y equal to 0 into the second guy, what do I get here?
3 times x minus.
Equals 0, so I get x is
0.
0 or
2.
2. So what points did I just get?
0, 0, and
Yeah, 0, 0,
2, 0.
and 2, 0. You guys see that? How to do that? Take one, solve it, and then start plugging them one at a time into the other one. You get multiple points, possibly, for each one. So now y equals -3. So something very familiar happens. Basically the same thing, really. If I make y equal -3, I get -6. I get -3 x times x minus 2. So I still get x equals 0, x equals 2. But now putting it together with the y, I get 0, -3, and 0. I'm sorry. I'm so sorry. 0, -3, and 2, -3. There it is. Okay, cool. I really don't want these critical points to feel to you as if they're coming out of nowhere. I mean, you can see where they're coming from. And there will be more than we're used to there being because this thing is all over the freaking place, whatever this thing is. And then finally, x equals 1. I'll get 1 times -1. So it all depends on this guy, right? Equal to 0, so y equals -3 halves. So I get the point 1, -3 halves. So there are my critical points. Maybe. I don't know if you guys have ever heard. Have you heard about? It's nearly impossible. In fact, some people think it is impossible to create a function that would find the lowest price airfare because of all the possible variables involved. So the same kind of math we're doing right now will work with stuff that I can't possibly graph because there are like 18 variables. But I still attack it with the same math. What really gets weird with 18 variables, all the freaking partial derivatives you got to do, but also it might look like it's a local max except for one direction actually goes above it, and you can't even imagine 18 dimensions. So the math gets really hard, but the math is basically the same. It's just more of it, right? Now that we got our critical points, what can we do? to figure out what happens at those critical points. Plug it into the D dude, right? And I forget, I don't think they actually tell you. Yeah, it's the discriminant. There you go, cool. Bottom of page 855, the discriminant, which makes it make sense for the D. They also talk about the matrix this guy comes from, the Hessian matrix. You don't have to know that. Don't worry about that. Just remember the formula. It's pretty easy to remember. So, for example, let's look at figuring out what this guy is. So I've got fx is here. Where do you go? Y plus 3. X minus 1. I've got fy is here. X 2y plus 3. To do the discriminant, I need fxx, fyy, and then fxy, which is the same as fyx, so it doesn't really matter which way you attack it. So what's fxx? Yeah, because this piece is 1 and these are constants, right? So you get 2y, y plus 3. What's fyy?
2x times x minus 1.
Yeah, derivative of this is 2 times this business here. And then finally, what's fxy? Yeah, what are you going to look at? What are you looking at, and what partial are you doing?
The 1.
So you look at this guy,
Yeah.
and you take derivative with respect to
1.
y, 11, right? So tell me again, what do you get? Now here you can bring it in and make this. If you want to, you can make
4, 2,
it makes it a little bit easier, so you don't have to do a product rule and put them all back together. So what's fxy going to be? 4y plus 6 times x minus 1. How are we doing so far? What's up? You're good? Okay. All right. So now to do that discriminant, you just have to evaluate the pieces at the point. And we're going to have to do it how many times? Well, 1, 2, 3, 4, 5. You have 5 points. And we have to do each of them, right? So if I look at the point 0, 0, that's a good one to start with. fxx at 0, 0 will be 0. I like it. fyy will be 0. fxy will be, I like it, negative 6. So then what's d at 0, 0? It's going to be 0 times 0 minus negative 6 squared, right? Just plugging into the formula, ffx, fyy minus fxy squared. Now I will say this about myself, and this is true in a lot of different places. I'm never totally careful about always putting the stupid point down, and hopefully you guys are okay with that. When I write this equation, it is here, but it means each of these is evaluated at that point. So what do you get? You get negative 36. So what situation am I in? We got d less than 0. We just got d less than 0, right? So it can't be 1 or 2. It's got to be the third one, d less than 0, which means it is a saddle point. I love it. So there's a saddle point at 0, 0. Yes?
Can you write down the steps? Because you did it for the first one, but you didn't do it for the rest.
Okay, step 1, critical points. There they are. Step 2, this guy, for each point. So there's really only 2 steps. There's a lot to it because you can have very many critical points. And just to do D is a bunch of second partial derivatives, so it is kind of long.
Can you always just plug in zeros?
Why did I plug in zeros? Because one of my critical points was 0, 0. So I have to evaluate D for each critical point.
So you gotta do that right there for every single point?
Exactly.
Oh my god.
Oh my God. Yes. All right.
You don't have to, you can walk out.
I would have been able to W on my freaking thing.
At any time, it's your decision. Yes. I like that. So, you know, you just keep going. If you do 2, 0. What's fxx for 2, 0?
0.
And it's still 0. What's fyy?
0.
For 2, 0, it's going to be 0 again. What's fxy?
Your calculator.
In this case, it's going to be positive 6. But my d is going to be fxx, fy. So 0 times 0 minus 6 squared, which is still negative 36, which is still less than 0. So at 2, 0, there is a saddle point. I think maybe that's enough of those. You guys, you just keep going, right? This is one thing that I do think I will give you on a test. Right? I am known for not giving you much of anything. I know that because you have to know this stuff.
Put one problem, it's basically 10 in itself.
I know, exactly.
Oh, that's true. I don't like it.
Guys, wait up. Did I make it sound like I was done?
We were hoping.
I know. I know. Let's say this. Who remembers when you did Calc 1, you talked about finding local maxes and mins. What was the next thing you did like right after that? Well, you did that hopefully during that because you could do local maxes and mins either with first derivative or the second derivative test. Absolute maxes and mins. And what normally is true when you're talking about absolute, remember, so you have to check all the critical points, but you have to also check endpoints. So in this case, now that's what it is if I have 2 dimensions, and I say I go from 1 to 4, and I have some function that does, you know, this here. I made it not very obvious here, but all. So this would obviously be an absolute min on the thing from 1 to 4. And it can do whatever it wants to outside of there. And this would be the location of a absolute max on that interval, right? So what's going to happen now in 3 dimensions? I'm not going to be able to just give you an interval because my inputs are now not numbers. My inputs are, what are my inputs now for 3 dimensions? What do we always write? F of what equals E? Yeah, my inputs are now, my inputs are points in the XY plane, right? So, I can't just talk about an interval of inputs. I have to talk about somehow a region of inputs. And yes, you can make a hard question just because you can define your region really stupidly, right? And I hate problems like that that say, the region that looks like the letter Z. No, screw that. Believe me. Bad teachers do really weird action. You normally just have very often you'll have a region that's circular. So they'll say something like, find the max, let's say absolute extrema. Yeah, Jeff, that's a word. Extrema for some function on the region x squared plus y squared less than or equal to 25 or something like that. Now just kind of absorb that for a second and see what if you see what I'm talking about. The only inputs I'm allowed to use have to be in that circle, right? So what are my endpoints now going to be related to? I don't have endpoints really.
Was the function across the circle?
No. Because this circle, where's this? The circle's in the XY plane and my surface is over it, right? Whatever this thing is my surface and it's hovering over my circle in the XY plane. It's like all the outputs for when I plug in those points, right? My endpoints are going to be the boundary of this region. And the boundary of this region is the circle itself, the very circle, not the disk, but the circle, the edge. You with me? A little bit? So this is the last thing I want to do. I want to do a problem like this, and then that'll be it, right? You guys are all like, shit. Man, I put my pencil away already, man. All right.
I don't feel like getting mind raped today.
You feel more like getting mind raped on Wednesdays? Is that what it is?
Yeah, it's Monday. Don't ruin Monday. I already have to go to work.
Not my words, by the way. I think somebody back there is like, holy shit, do you know? He said that. All right, this will be, yeah, let me do example 6, because I'm going to do it a little bit differently than the book does it, just to make a point for later. Example 6 gives us this. And they want to know what's the absolute max and min on the region. And I hate the fact that they use the, and this only makes sense in a way, they use the letter R for region, but that of course looks like real numbers. So it's kind of sucky, but oh well. So on the region defined by x squared plus y squared less than or equal to 4. So this is example 6, page 858 at the bottom is where it starts. I'm going to do it a little bit different way than the book does it, just because. So here's how this goes. Yeah.
Sorry, is this still 12.8?
Still 12.8, yeah.
Okay.
What do I do, of course, first? Because the main idea here is I've got to check what and check what. I've got to check critical points. Of course, that means you've got to find them.
Oh.
And I've got to check the boundary somehow, right? The boundary of my region. Okay, how we doing?
You have 2 minutes.
So how do I find my critical points? Jasmine.
I hate you.
Time is ticking away, and they're all depending on
FX, FY.
All right, FX is
I don't know.
2x minus 2. 2x minus 2.
you're holding this up. FY,
Do you not see my red face right now?
2y plus 2.
Set those equal to 0.
I love it. Right. And they're not always going to be this nice, of course. Here they both have just the one variable in there, and we saw one earlier. So this is going to be really nice. I'm only going to get how many critical points here. And it's actually very directly defined. What's the answer here? X is 1, and here? Negative 1. So I just got one critical point here. How's that? Maybe I can get that in a minute left. So there's my critical point. Right? And the nice thing here is, the other really nice thing about this, and I don't know if you remember this, absolute maxes and mins compared to local maxes and mins were awesome. Because I only care about the output of them. Do you remember that? Just look, just put them all in the function. The biggest number is the max, the smallest number is the min. Sweet. Do I have to do the D business? No, I don't care if it's a freaking saddle point or whatever. I just care about where the biggest thing is and the smallest. So what is f of 1, negative 1? Neat. All kinds of answers.
7.
So you get 2 minus 2 is 0.
I was doing it in my head.
Minus 2 is negative 2 plus 5 is 3.
Wow.
Good job.
That was so bad.
Now here's where I differ. Now, I really want you guys to see this before you walk out on mass in the right time. Here's the beautiful thing about this. Here's my what's my boundary going to be? What's my interval? The endpoint's going to be. In this case, it's a boundary. It's x squared plus y squared equals 4. Right? That's the boundary. Less than or equal to is the whole disk area, right? And I want to look at this function here. Let's see if you guys can understand what's going on here. What's really nice here? I mean, think about it. I want to only use points that are on this boundary. Therefore, this is 4, minus 2x plus twice, well, solve for y, right? Solve for y, and then I end up with one variable. See if you see what I'm saying here, I don't know.
Equal to 0 or
So if you solve for y, you get, I know you get plus or minus here, right? Plus or minus, oops, I need it up there, plus or minus square root of 4 minus x squared. So you get 9 minus 2x plus twice this. That's f of x really here now, right? It's really only dependent on one variable. What do you know so far? Then you take f prime, you find out what its critical points are, and you see what the value of the function is there. You guys got it with me here? No?
We're done.
No, I am, I
That's
still
fine.
wanna do it.
So we'll pick it up there next time.
Yeah, call me, Jack, come on, I'm ready to go.
Once a year.
I just
Here
don't
we
want
can
to-
just use Calc 1, right? Take
Yeah,
it
yeah.
right there.
This root is not that bad. Comes up a decently easy function. What they do in the book is actually nice because they take it to parametric. They take it to theta. Because there is one problem with my method. You actually have to do it the other way, which is replace the x's with the y's to be able to catch everything. Because if you only do it with the x's, you might only catch one side of it.
But then I have to do it twice because I have plus minus, right?
Yeah, the plus minus at the end is not going to bother you because you're going to end up squaring things anyway, I think, if I remember right. Because you want to set it equal to 0 anyway. Yeah. Yeah. Oh, yeah. Yeah. I had to push the last one back, so.